If you've been to an airport lately, you've probably noticed that air travel is becoming increasingly congested. Despite frequent delays, airplanes still provide the fastest way to travel hundreds or thousands of miles.
Welcome to our YouTube channel Random, and today we are going to watch a video on
all about Maglev train in detail. Before that, we would like to tell you that the only alternatives to airplanes, feet, cars, buses, boats and conventional trains are just too slow for today's fast-paced society. However, there is a new form of transportation that could revolutionize transportation of the 21st century the way airplanes did in the 20th century. A few countries are using powerful electromagnets to develop high-speed trains, called Maglev trains. Maglev is short for magnetic levitation, which means that these trains will float over a guideway using the basic principles of magnets to replace the old steel wheel and track trains. Electromagnetic suspension, EMS. If you've ever played with magnets, you know that opposite poles attract and like poles repel each other. This is the basic principle behind electromagnetic propulsion. Electromagnets are similar to other magnets in that they attract metal objects, but the magnetic pull is temporary. You can easily create a small electromagnet yourself by connecting the ends of a copper wire to the positive and negative ends of an A, C or D cell battery. This creates a small magnetic field. If you disconnect either end of the wire from the battery, the magnetic field is taken away. The magnetic field created in this wire and battery experiment is the simple idea behind a Maglev train rail system. Above is an image of the guideway for the Yamanashi Maglev test line in Japan. The big difference between a Maglev train and a conventional train is that Maglev trains do not have an engine, at least not the kind of engine used to pull typical train cars along steel tracks. The engine for Maglev trains is rather inconspicuous. Instead of using fossil fuels, the magnetic field created by the electrified coils in the guideway walls and the track combine to propel the train. The Maglev track, the magnetized coil running along the track, called a guideway, repels the large magnets on the train's undercarriage, allowing the train to levitate between 0.39 and 3.93 inches, 1 to 10 centimeters, above the guideway. Once the train is levitated, power is supplied to the coils within the guideway walls to create a unique system of magnetic fields that pull and push the train along the guideway. The electric current supplied to the coils in the guideway walls is constantly alternating to change the polarity of the magnetized coils. This change in polarity causes the magnetic field in front of the train to pull the vehicle forward, while the magnetic field behind the train adds more forward thrust. Maglev trains float on a cushion of air, eliminating friction. This lack of friction and the train's aerodynamic designs allow these trains to reach unprecedented ground transportation speeds of more than 310 miles per hour, 500 kph, or twice as fast as Amtrak's fastest commuter train. In comparison, a Boeing 777 commercial airplane used for long-range flights can reach a top speed of about 562 miles per hour, 905 kph. Developers say that Maglev trains will eventually link cities that are up to 1,000 miles, 1,609 kilometers, apart. At 310 miles per hour, you could travel from Paris to Rome in just over 2 hours. Germany and Japan are both developing Maglev train technology, and both are currently testing prototypes of their trains. The German company Transrapid International also has a train in commercial use, although based on similar concepts. The German and Japanese trains have distinct differences. In Germany, engineers have developed an electromagnetic suspension EMS system, called Transrapid. In this system, the bottom of the train wraps around a steel guideway. Electromagnets attached to the train's undercarriage are directed up toward the guideway, which levitates the train about 1/3 of an inch, 1 centimeter, above the guideway and keeps the train levitated even when it's not moving. Other guidance magnets embedded in the train's body keep it stable during travel. Germany has demonstrated that the Transrapid Maglev train can reach 300 miles per hour with people on board. How Maglev trains work. Japanese engineers are developing a competing version of Maglev trains that use an electrodynamic suspension, EDS. system, which is based on the repelling force of magnets. The key difference between Japanese and German maglev trains is that the Japanese trains use supercooled, superconducting electromagnets. This kind of electromagnet can conduct electricity even after the power supply has been shut off. In the EMS system, which uses standard electromagnets, the coils only conduct electricity when a power supply is present. By chilling the coils at frigid temperatures, Japan's system saves energy. However, the cryogenic system uses to cool the coils can be expensive. Another difference between the systems is that the Japanese trains levitate nearly 4 inches, 10 centimeters, above the guideway. One potential drawback in using the EDS system is that maglev trains must roll on rubber tires until they reach a liftoff speed of about 62 miles per hour, 100 kph. Japanese engineers say the wheels are an advantage if a power failure caused a shutdown of the system. Germany's Transrapid train is equipped with an emergency battery power supply. Also, passengers with pacemakers would have to be shielded from the magnetic fields generated by the superconducting electromagnets. The Inductrack is a newer type of EDS that uses permanent room temperature magnets to produce the magnetic fields instead of powered electromagnets or cooled superconducting magnets. Inductrack uses a power source to accelerate the train only until it begins to levitate. If the power fails, the train can slow down gradually and stop on its auxiliary wheels. The track is actually an array of electrically shorted circuits containing insulated wire. In one design, these circuits are aligned like rungs in a ladder. As the train moves, a magnetic field repels the magnets, causing the train to levitate. There are 2 Inductrack designs, Inductrack I and Inductrack II. Inductrack I is designed for high speeds, while Inductrack II is suited for slow speeds. Inductrack trains could levitate higher with greater stability. As long as it's moving a few miles per hour, an Inductrack train will levitate nearly an inch, 2.54 centimeters, above the track. A greater gap above the track means that the train would not require complex sensing systems to maintain stability. Permanent magnets had not been used before because scientists thought that they would not create enough levitating force. The Inductrack design bypasses this problem by arranging the magnets in a Halbach array. The magnets are configured so that the intensity of the magnetic field concentrates above the array instead of below it. They are made from a newer material comprising a neodymium-ion boron alloy, which generates a higher magnetic field. The Inductrack II design incorporates 2 Halbach arrays to generate a stronger magnetic field at lower speeds. Dr. Richard Post at the Livermore National Laboratory in California came up with this concept in response to safety and cost concerns. The prototype tests caught the attention of NASA, which awarded a contract to Dr. Post and his team to explore the possibility of using the Inductrack system to launch satellites into orbit. While maglev transportation was first proposed more than a century ago, the first commercial maglev train made its test debut in Shanghai, China, in 2002 using the train developed by German company Transrapid International. The same line made its first open to the public commercial run about a year later in December of 2003. The Shanghai Transrapid line currently runs to and from the Longyan Road station at the city's center and Pudong Airport. Traveling at an average speed of 267 miles per hour, 430 kph, the 19-mile, 30-kilometer journey takes less than 10 minutes on the maglev train as opposed to an hour-long taxi ride. China is building an extension of the Shanghai line that will run 99 miles, 160 kilometers, to Hangzhou. Construction is scheduled to begin in fall 2006 and should be completed by the 2010 Shanghai Expo. This line will be the first maglev rail line to run between 2 cities. Several other countries have plans to build their own maglev trains, but the Shanghai Airport line remains the only commercial maglev line. US cities from Los Angeles to Pittsburgh have had maglev line plans in the works, but the expense of building a maglev transportation system has been prohibitive. The administration at Old Dominion University in Virginia had hoped to have a super shuttle zipping students back and forth across campus starting back in the fall semester of 2002, but the train remains motionless while research continues. The American Maglev company is building a prototype using similar technology in Georgia that it plans to finish by fall 2006. Like our video if feel it was best explained. Comment down below your thoughts on Maglev Train. Subscribe to our YouTube channel for more and press the bell icon for more updates. Thank you everyone, you were awesome.